Hello, everybody. My name is Boris Botvinnik from University of Oregon. I'm happy to be part of this workshop in honor of Misha Gromov. And the work I'm about to present in many ways is inspired by his work, by the work of Misha Gromov. So the title of the talk is Topology of Spaces and Moduli Spaces of Metrics with Positive Scalar Curvature. I would like to start with notations. This is first part, introduction. Usually we work with a compact manifold without boundary, and the notation will be W for manifold. Now the R of W is the space of all Riemannian metrics in the smooth topology. Also, I would like to mention right away that this is a space which is contractible, not just contractible, it's convex. It's easy to see that any two Riemannian metrics you can connect by the interval, and this is why it's convex. So we'll use abbreviation PSC metric G, which means that metric G, Riemannian metric, has scalar curvature positive. This will be notation SG for scalar curvature. We'll be interested in the subspace of metrics of positive scalar curvature, which turns out to have quite non-trivial topology. If this space, if manifold W has boundary, non-empty boundary, then we have to be a little bit more careful, and we denote by R of W space of all metrics on W which are product near the boundary, product metrics near the boundary for some metric H. Notice that if we deal with the metric G, which has positive scalar curvature, then metric H, which is a restriction of G on the boundary, also has positive scalar curvature. This is why we have a restriction map from all metrics of positive scalar curvature on W to metrics on positive scalar curvature on the boundary. It is actually important and quite non-trivial fact that this is Serre fiber bundle. I would like to discuss existence of metric of positive scalar curvature just a little bit in order to introduce important and necessary constructions. And for the purposes of this talk and in general, I would like to restrict myself only to oriented, simply connected compact manifolds of dimension at least 5. The reason is very simple. For this particular class of manifolds, the existence problem is completely resolved. It turns out in differential geometry, it turns out that there are several fundamental questions which have completely different answers and technology for two classes: spin and non-spin. Let me remind, just in case, that manifold smooth compact oriented manifold W is spin if a second Stiefel-Whitney class is equal to 0, and non-spin if it's not equal to 0. And in the non-spin case, there is a following theorem by Gromov from 79, that W be a closed compact non-spin simply connected manifold of dimension at least 5, then it always admits a metric of positive scalar curvature. Now, in the case of spin, the second, well, in order to state second result, we have to remind a couple of things. So we take a metric G on manifold W, which is spin. Then there exists a canonical real spin bundle SG, and Dirac operator acting on the space of spinors, actually sections of this bundle. And Lichnerovich result formula back from 1960 is that square of Dirac operator is equal to this Laplacian, spinor Laplacian, plus 1/4 of scalar curvature. In particular, it means that if scalar curvature is positive, then our operator is invertible. In modern terms, it means that index of this operator has to be equal to 0. Has to be equal to 0. Now, in terms of contemporary mathematics, I would like to describe this in the following way: that if we have a manifold W of dimension G and spin, and take metric G, then we look at Dirac operator, corresponding Dirac operator, then normalize it, and then this lands in the space of all Clifford D linear Fredholm operators. This space, which basically is space of all Dirac operators, is very well understood. In particular, this space classifies real K-theory in the following sense, that Qth homotopy group of this space of these Fredholm operators is the same as KOD plus Q, when D is perhaps the dimension of the manifold. Then we have the following construction. We start with manifold W, we choose any metric G, and we look at the image of this Dirac operator in this space and look at the path component. And path component gives me pi, it's a pi 0 of this one, and this gives element in K-theory. And it is quite clear that this construction does not depend on the metric G, because if we have any other metric G prime, then there is an interval between metrics between these two metrics G and G prime, and we have to land in the same path component under this map, alpha. The next step is to understand that if we have the following, if we have W and W prime, which are related to each other in the following sense, that their boundaries of the same spin manifold, then the index theory tells us that in this case, and yes, let me have a notation, omega spin D, if dimension of manifolds D, then so this is a class, spin Bodism class of manifolds. And then index theory tells us that there is this map alpha does not depend on the choice of Bodism class. In other words, from our perspective, what we have manifold W, and then we can look at its Bodism class in omega spin D, and look at the image of this class in K-theory, KOD, and if this is non-zero, then there is no metric of positive scalar curvature on W. Okay, so now let me go back to these two fundamental results by Gromov and Lawson. So first theorem, non-spin, and second theorem, spin. And let me look at the second theorem now, and which says the following: that W is a closed spin simply connected manifold of dimension at least 5. Then there exists metric of positive scalar curvature if and only if alpha of W is 0 in KOD. If you think about these both results from the viewpoint of geometry, so there is a natural question how you would find such a metric of positive scalar curvature, even if you know. So there's a very simple topological condition here that it's non-spin and there is a metric of positive scalar curvature. Or you check everything here that alpha of W is 0, but you still have to find such a metric. And it is really fundamental issue because if you have a space of all metrics of Riemannian metrics are of W, then if you have your manifold W, which comes say with some metric G, but space of metrics of positive scalar curvature may be far, far away from this given metric G. So so there is no kind of any reasonable way to kind of find a path from this given metric G to metric of positive scalar curvature. This is why kind of the real proof of these both theorems require topological methods, namely surgery. So-called surgery lemma. This is surgery lemma. Let me explain what is surgery just, in the following cartoon, that if we have a manifold W, and this W I will present as a just sphere, SG, and if we have S dimension P cross D dimension Q plus 1, it's a tubular neighborhood of this sphere dimension P, and this is we call codimension. Then what we can do, we can delete this tubular neighborhood and attach a handle which is dp plus 1 cross sq, and we'll get new manifold which we call w prime. In this case, in the case of sphere sd, we'll recover manifold sd minus 1 cross s1. Okay, and then the lemma, surgery lemma says that if we have a priori metric G of positive scalar curvature, then what we can do, we can construct metric G prime on new manifold W prime with metric G prime. Okay, this why does it help? Why does it help? So let me actually explain a little more. Now, if we have our manifold W, then if we have a Bordism to a manifold W prime, not necessarily spin, some oriented Bordism in this case, and or in this case, in the first case, and spin Bordism in this case, then what we can do, if we can find in the Bordism class a manifold W prime with a nice metric of positive scalar curvature, then what we can do, we can use this lemma to push metric W G prime through this Bordism X back to manifold W. And then it's actually, there's one more step here, which is really interesting. What's about if we look at the all space of metrics of positive scalar curvature on W and space of positive scalar curvature metrics on W prime? Is there a relationship between these two? And the answer is yes, there is a relation. Both spaces are homotopy equivalent. In this case, I don't state kind of most general theorem. I just, I adapted for the case we really need here. And this is done by Chernish back in 2006, and then by Walsh in 2010, and also by, so there are some more even more there's a detailed paper by Ebert and Frank. So if we have two manifolds are simply connected and cobordant spin manifolds, then these two spaces are homotopic. And also there is a corresponding result for manifolds with boundary. Then these two spaces with a given metric H, in this case we have a following kind of result that there is a Bordism on the interior, and there is the same metric on the boundary. Okay, so in particular, it works for spin manifolds, and if we have two simply connected spin manifolds, dimension at least 5, then they have exactly the same up to homotopy spaces of metrics of positive scalar curvature. There's a new result by Ebert, Kordash, and Wilmer, very recent, a couple of months ago, that if that in fact the homotopy type does not depend on the Bordism class, only on the dimension D for simply connected spin manifolds of dimension at least 6. And there's a similar result for manifolds with boundary. And so it gives some hope that there is a way to understand homotopy type, at least something about topology of the spaces of metrics of positive scalar curvature. Let me convince you that the space of metrics of positive scalar curvature on S7 is not trivial. So we look at pi0, we look at path components. We start with the Bot manifold of dimension. This is a manifold with simply connected spin manifold, dimension 8. And also alpha genus, alpha invariant, which is the same as A hat genus, in this case is equal to 1. In particular, it means that there is no PSC metric. And also this manifold is well understood. Actually there are many examples of such manifolds, but there are some metrics with Ricci flat metric on such manifold and so on. But now what we do, we take this manifold B, Bot manifold, and delete two disks of dimension 8, and then we have one sphere on one end, dimension 7, and the other is sphere on the other end. Now, what we can do now, we start with metric G0, standard metric on the sphere, and push this metric through the Bordism, as which is allowed by Sergio lemma, and we'll construct metric of positive scalar curvature on the other end, so call it G1. And now G1 is not, you cannot make isotopy to G0. Why? Because if you would have such an isotopy, you would be able to put a cap to extend this metric to the disk of dimension 8 here. And this one is actually also, we can extend to the disk of dimension 8 because this is just standard metric on the sphere of cell 7. And then in this way, you would get a metric of positive scalar curvature on the whole both manifold B, which is not possible. And if you iterate this construction, then you recover Z different path components. You can detect Z different path components. And the main question that we address here, what is the topology of this space for spin manifold W? Right away, I would like to address the open problem that the topology of this space metric of positive scalar curvature for non-spin manifold W, we know nothing essentially except that the fact that it's non-empty. And the conjecture, which I hope fails, that this space of metrics of positive scalar curvature is contractible for non-spin simply connected manifolds W. I hope it will fail. Okay, now to understand topology of this space, we have to introduce some, a little bit of technology. Namely, if this construction is due to Nigel Hitchin. If you take some metric G0 and declare it to be a base point in the space of metrics of positive scalar curvature, then what we can do, we can take any other metric G and take a path, so just a straight interval of metrics between G0 and G. And then, so what we see that for each metric GT gives a Dirac operator, Dirac operator corresponding Dirac operator. And what we get a path of Dirac operators. And it's important to observe that it starts and ends at the subspace of all Dirac operators, which are invertible. And it's a very important theorem that the space of all invertible Dirac operators is contractible. Now, what we can do, we can just take our hand and can put and smash our subspace of invertible Dirac operators, and then we'll get the following. For each metric G, what we get a loop. Of course, this map is up to homotopy. Get a loop of in the space of all metrics of all Dirac operators, Fredholm Dirac operators. And so this gives us a map from the space of metrics of positive scalar curvature to the loops of on the space of Fredholm operators. This map is defined up to homotopy. So in particular, we obtain a homomorphism from the kth homotopy group of metric of positive scalar curvature W to kth homotopy group of the loops, which is nothing but K or K plus G plus 1. And G, I remind again, it's a dimension of W. Now, there is another classical way to construct index difference map, which is again due to probably Gromov and Lawson. If we start with the metric G0, then we take as a base point, again, take metric G and take the same interval of metrics, then we can put this metric on the cylinder W cross I with the metric G bar which is gt plus dt squared. Now it gives a Dirac operator on with Dirac operator on the cylinder with IT Topology boundary conditions near the along the boundary, and we get a map again, so which gives index. We take index of this Dirac operator. It lives, of course, in space Fred D plus 1, 0, which is actually homotopy equivalent to the loops of this Fred D0. And we get this second map. And index theory tells us that these two maps are homotopy. Now, and then I would like to consider this map again and choose some base point. And then this is the theorem I would like to explain in the second part with more detail, that which is done by myself, Johannes Siebert and Oscar Renda-Williams back in 2014. So let W be a spin manifold with dimension at least 6, and G0 is some base point. Then this map in homotopy is non-zero. Homomorphism is non-zero whenever the target group is non-zero. Let me just say a few words here. Notice that if it's non-zero on Z2, that it means that it's onto. If it's non-zero on Z, it means that a priori it may go to some generator times some number. So it's maybe not surjective. But what we prove that it's actually surjective in degrees up to some crazy number like 500 when a dimension of D has 500 digits. Otherwise, it is reduced to some non-trivial number theoretical question. Now, couple of important remarks that there is a different proof given by Nathan Perlmutter, who used he advanced Morse theory to prove it, and this result extends. So previous result done before that by Crowley and Schick and Hanke, Schick and Steinle back in 2012 and 2013, and there are several. There are much stronger results for non-simply connected spin manifolds, which are done recently by Johannes Siebert and Oscar Renda-Williams. And thank you very much. This is the end of the first part.